As an example of relative motion, I think a very useful example is considering the road moving. Okay, that sounds very practical, right? The road is moving. How often do you encounter that? You may not encounter it very often, but it really isn't that extreme. It's not much of an extrapolation of thought, because an example of a moving road is a boat in a river. The river is the road and it's moving. So I have a very realistic scenario here of a bear driving a boat. I guess that's a bear. I don't know what it is. Well, the subscript convention we'll use is B for boat, S for shore, W for water. So here is my river. Usually I have rivers pointing vertically and the water moving up or down. But right now I'll have it flowing sideways and the water is moving to the left. So here's the river direction. It's a moving road, and we're going to put the vehicle in it, namely the boat. So here's the boat. And this boat, we're going to direct at an angle of 30 degrees with respect to the shore. So here's the shore, and 30 degrees from that, 30 degrees from the shore, is the direction that the boat is heading. So, and it, by the way, this boat, when you motor it up, when you turn the throttle and get that motor going, it'll move at 10 meters per second. That's the velocity of the boat with respect to the water. If you put this boat in a lake and hit the throttle, you will move at 10 meters per second. That's the idea. So we're going to assume full throttle, full speed, and just recognize that this vector is not going to be the actual motion of the boat from the point of view of the shore. You're not going to see the boat go like this because the water's moving and it impacts what the boat is doing. So 10 meters per second, this is how fast the boat moves with respect to the water. And again, the water is moving. So here's our vector equation that we're going to be consistent with. The velocity of the boat with respect to the shore. You want to see what the motion of the boat is standing here on your little hind legs on the shore of this river. So let's construct, well, first of all, let's define the equation correctly. Outer subscripts match. So we have velocity of boat with respect to the shore is boat with respect to the water, first B right there, plus water with respect to the shore, that motion, and the outer subscripts match. So we're good. So we're going to add those vectors. Well, we already have this one, boat with respect to the water. We just have to add the water with respect to the shore. What is the velocity of the water with respect to the shore? You're standing here observing the water. It already says, and this isn't a vector, but I'm just showing the direction of flow. So here it is. Now I hadn't told you what the actual motion, the velocity of the water is, but I'm kind of picking this uniquely here. Let's say it's exactly what I show here. Velocity of the water with respect to the shore. Our answer is just adding those two, and there it is. Now that should match your intuition. If you think of the water flowing down and the boat, well, if the boat pointed straight across, it would get drawn downstream from the flow of the water. So you have to point upstream, and then the water flowing down kind of tries to push it down. So we've chosen these so that the boat goes straight across. So that's what my note is here. The boat will go straight across the river if we choose the angle correctly, really so that this say rightward component equals the motion of the water itself. Then those will cancel out, and you'll get the boat moving straight across. If we angled it a little bit more, then we would actually be drifting downstream. If we angled it a little steeper, then we would be drifting upstream as we moved across. Does that make sense? So at 30 degrees with respect to upstream or the shore, What's the velocity of the boat from the point of view of an observer on the shore, and how fast is the river flowing? Those are very readily obtainable. You will notice we have a right triangle here, but be careful how you handle this. For instance, the hypotenuse is not the resultant. The resultant is the addition of the hypotenuse and this other side to give us this for the resultant. So we got to determine an appropriate scale. I want to do this graphically. We could do it either way, but I want to do it graphically for intuitive understanding. So we're going to construct an accurate vector diagram with a scale of 1 centimeter equals, well, it's got to fit on the page. We'll pick 1 meter per second. So let's construct our vectors. Here's our reference line, and I'm going to start at that dot over there, bring in the 6 and 1, and measure the angle, 30 degrees, right here. So we can put a dot there and then construct it the right length. What's the right length? Well, based on our scale, it would be 10 centimeters. 10 meters per second, velocity of the boat with respect to the water. 30 degrees. The boat goes straight across now. We know the boat goes straight across. That was in the discussion, or it will usually be explicitly stated. So we construct a reference line in the correct direction, namely that from here we're going straight across. So do a perpendicular line to the reference, and that's the line along which the resultant vector will lie. So we know the river direction, and we know when we add the river vector to this one, it will end up hitting this reference line. So let's go through the tip of the boat velocity vector, since that's the vector that's going to be added to the water velocity vector. So here's the reference line, and we're pretty much done with our construction. Draw on the vector of the water, and if we measure it, we discover it's about 8.6 centimeters, corresponding to 8.6 meters per second. And the crowd is happy. The small crowd, nevertheless. Those that are observing this are happy. We got the resultant, and we measure it. It's about 5 meters per second, and we've accomplished our purposes. Now, a quick trig check on this example is readily forthcoming because of the right triangle nature of this. So if we do this real quickly, we see a 30-degree angle here, and here's the various vectors: velocity boat shore, velocity water shore, velocity boat water. We know the hypotenuse, and we know this angle. So the sine of 30 is opposite over hypotenuse, which is VBS over 10. So VBS is 10 sine of 30, or 5 meters per second. Yes! And then as far as the water vector goes, the velocity of the water with respect to the shore, we know that'll emerge from the cosine, which is VWS over 10. So VWS is 10 cosine of 30, or 8.7 meters per second. And there it is, an example of relative motion of a boat in the water. And I'm hoping that these vectors are not seeming so mysterious anymore.